Okay, so I want to talk about the concept of energy conservation. We talked about the work energy theorem. The work energy theorem, which is the total work done on a body or system of bodies, is the change in kinetic energy. And we know that the work done by force is F dot ds, and the kinetic energy, that's a definition, is the energy of motion, mv squared. And so we can go ahead and apply the work energy theorem to any problem, which, never mind what I was about to say. But I want to think of this in a different form. So what we're going to do is we're actually going to write down this in a different form. It's really the same equation, but it gives us the concept of energy conservation. Because work is not energy. Work, what this tells us is that work can be changed into energy, or you have to do work in order to get kinetic energy. You have to do work in order to get motion. Motion being speed. So let's look at this from a different point of view. I'm going to take that work total and I'm going to say, okay, well, so you know that we've got such a thing as conservative forces and non-conservative forces, and that's it. There's only conservative forces and there's non-conservative forces. And I'm just going to break the work up into the conservative forces and non-conservative forces and say that, okay, the work done by conservative and non-conservative forces is changing kinetic energy. There's no other kind of force, so that's just a restatement of the same thing. Just differentiating between the things like, for example, gravity. Try to think of another conservative force. The spring force is a conservative force. I'm not entirely sure if tension is a conservative force. It doesn't matter. If we don't know, we can always just group it into the non-conservative force category. Maybe we'll see why. Non-conservative force, the only one we really know of as non-conservative force is friction. We know that friction is non-conservative force, so we showed that. Okay, so that's all we need to start with. Any force can go into one of these categories. So here's what we're going to do next. We're going to define a new variable. And you say, why are we defining a new variable when this works for everything? Which it does, but it's because of its a really important concept. And the variable we're going to define is called potential energy. The potential energy can be written as PE, just like K. KE is kinetic energy. And sometimes, by the way, we just write K for kinetic energy. And then sometimes we just write, instead of P, because P is reserved for power and momentum, we actually call potential energy U. So this is just notation, right? Just the variable we use. So we don't use P for potential energy, we use U. But I'm going to pretty much probably stick with PE and KE so we don't forget what they are. And what we will find, or what we have already discussed a little bit, is that for every conservative force, we can talk about the fact that the work done by that conservative force must change the potential energy of a body. But the potential energy is the energy due to position. For a mass, if we lift that mass up from the ground, we have now given it the potential to get kinetic energy, right? So it's the fact that we have changed its position that it's got the potential to get energy. So for every conservative force, we can actually define, we can say a conservative force changes the potential energy. And we actually define, for reasons which are pretty obvious in a second, we define the work done, well, not for, I mean, because if we lift something up, gravity does negative work, we've given it positive potential energy. We've given it the potential to get kinetic energy. So the work done by a conservative force is defined as minus the change in potential energy due to that force. So the reason why I put this definition that I just wrote in quotes is because we're saying that, yeah, there's a total work done by conservative forces, but each force has a conservative work that can be defined as minus the change in potential energy due to that force. And then we just add up all those potential energies. Okay, so what we end up getting, if we define this, and we plug it into there, what we end up getting is this, and then we add the change in PE to both sides, get this. So this is still just the work energy theorem, but it's sort of the work energy theorem stated in a different way. This says that if non-conservative forces do work, then they will change the sum of the Ke plus Pe. I don't know if that makes, if that gives you any farther conceptual understanding, but let me take it a step further and say, if there is no non-conservative work, or if there are no non-conservative forces, e.g. friction, that's the only one we know of so far, therefore the work done by non-conservative forces is equal to zero. Therefore, that tells us that the kinetic energy, the sum of the change in kinetic energy plus change in potential energy, is zero. That tells us that the sum of this doesn't change. And we can define, right, kinetic energy is the energy due to motion, potential energy is the energy due to position, and we can define Ke plus Pe. We're going to define yet another variable, which is called the mechanical energy, or the total mechanical energy. We often use the word total mechanical energy, but delta E. And so this says that 0 equals, whoops, I was actually starting to skip an algebraic step, but if we take this equation and we write delta Ke as Ke final minus Ke initial, delta Pe as Pe final minus Pe initial, we can rewrite those. We can reorder these terms, and what we find, this tells us that the total mechanical energy final minus the total mechanical energy initial is equal to 0. So therefore, 0 is equal to the change in total mechanical energy. So what have we said? We have said something extremely important in all of science. If there are no non-conservative forces, e.g. friction, that tells us that the mechanical energy does not change. Delta E is equal to 0. It doesn't tell us the mechanical energy is 0. It tells us the mechanical energy doesn't change. Careful, because many of you will make this mistake and say, oh, this means that E equals 0. That is not true. This tells us that it doesn't change. Delta E is 0. It doesn't change. Back to the original work energy theorem, we now have, right, I had said if WNC is 0, then you get 0 equals change in E. Well, actually, if it's non-zero, then this is just the work energy theorem, just rephrased. We have included the conservative forces on the right-hand side, where, it used to be work equals change in kinetic energy. This is the work energy theorem rephrased. And then if WNC equals 0, therefore, we say 0 equals delta E. E does not change, and that means E is conserved. The total mechanical energy of an object or of a system is conserved. So the concept here is, if there are no non-conservative forces, the energy of a system is conserved. And this concept of energy conservation is so important. Energy conservation in science is not turn out the lights when you leave the room to save energy. That's saving energy for later. But the fact that energy is conserved tells us that energy is not created or destroyed. It is just changed in form or to another body. And what do I mean by that? This concept of energy is conserved tells me that that energy is only changed from one form to another, potential energy to kinetic energy to potential energy, or it might be transferred to another body. And that's really where this non-conservative force comes in. That's really where it comes in. Because if you have friction, then you're sliding your dog across the floor because the dog doesn't want to go out, and you're pulling it on a leash. And if there's friction, the energy that you're giving the dog when you're pulling it across the floor is going away, right? You're not getting the dog moving. Where is it going? It's going into the floor because of the friction of the floor. So this concept that energy is conserved says energy is not created or destroyed. It is only transferred from one form to another, potential energy, kinetic energy, or to another body, usually through the non-conservative work, right, the work done by another body that's not in your system. So it's a really important concept. We'll do some examples coming up. Just keep in mind, this is just a concept. This is still just the work energy theorem. The other thing I want to do before we do some examples is to talk about the concept of heat.